Hey everybody, welcome to lecture number 22. This is my personal favorite topic, how to be wrong. When we do all kinds of data analyses, what we are obviously striving to do is not to be wrong. But I think if what you want is to eliminate mistakes, it's probably really a great idea to just give yourself some time to study how people do make mistakes. If you listen to all the horror stories, then you can get an idea of what not to do. So how to be wrong is, as I said, basically my favorite topic. And I love stories of data disasters. So if any of you find some amazing studies in case studies in failure, then I would love to hear about them. So please send them my way. But in the meantime, it's my turn to send you some studies in case failure. So today we're going to talk about, there we go, errors of measurement, errors that stem from analysis, errors that come from broken tools, or borked tools if you're from my generation, errors of human cognition, and errors that come from a lack of ability to communicate. So we're going to lead off with the measurement problems. So all this data that we have comes from somewhere, right? There is a tool, a device to measure things. And all measurement devices have some sort of error associated with them. So it's your responsibility as the person using these numbers to have an idea of what are the limitations of the tool that's producing these measurements. Okay? Like you've probably had some experience with a tape measure, and you know how it's marked in 16ths of an inch. Maybe it's marked in 30 seconds, but good luck using it precisely, right? So the tape measure has an inherent error that you can't get more precise than. Just holding the tape steady and still and even across something is inducing a kind of error. So you have an inherent limitation on how precise you can be in these measurements. Now, if something is precise, that means that it's close to the actual value. Sorry, I said that wrong. If something is precise, it means that all the times you try to measure something, you get basically the same answer. So a tape measure is not very precise. You're going to be off by a 16th of an inch or a 32nd, or maybe by a full half inch if you just don't get the tape all laid out flat, right? So the tape measure is not a precise measure. Assumedly, it may be relatively accurate though, right? Because the inches marked on the tape, they are marked by a machine that is assumedly very, very accurate. So when something is accurate but not precise, the average measurement is about right. So if you take a tape measure and you measure something 10 times, and you take the mean of all those measurements, you're probably going to come up with a better measurement than you started out with. Another example of a tool that's like that is GPS. So the satellites that tell your phone where you are at, they have built into them an error of on the neighborhood of 20 or 30 meters, at least for civilians like us. Okay? But if you hold still for a dozen seconds with good GPSs now, right, then you will get a much more accurate measurement of where you are. But if you're in a car, your error is going to be more on that order of 20 meters as you're driving 40 miles an hour down the street. So accurate things, the average is close to true. But maybe they're not precise. Maybe you've got a big spread of 20 meters, right? Maybe you've got something which is precise but not accurate. So you've got a tool which has a systematic error in it. So your measuring stick is a little short. Okay, you've got a set of calipers. You probably don't know what calipers are. You've got some sort of measuring device which is got a systematic bias in it. It always measures too short. Okay, but it's a very, very accurate measuring device. So you end up with this whole situation like we have here where the grouped shots are tight, but they're not on the target. So, so precision instruments can be wrongly calibrated. Oh, like a good example is your bathroom scale. You know, when you step onto it and you've got a moment where it's got to tear out, it's got to find out what 0 is. If you put something on the scale at that moment, you're going to get a wrong error systematically, but you'll have a precise measurement. So, all right, it's your responsibility to know what's generating these numbers, to understand the kinds of error it has, because that will influence the kinds of analyses you can do with it. Now, another interesting problem in measurement is, are we measuring the things that we actually care about? Or are we just measuring the things that are convenient? So the story of the lamppost or the drunkard search is a story which starts with a police officer walking on his beat and comes across a man on his hands and knees looking around on the ground. And he comes up to the man and he realizes the man is drunk and asks him what's wrong. Guy says, oh, well, I lost my car keys, so I'm looking for them. And the policeman is very kind and helps the drunkard look for a long time. But they can't find anything. So after a few minutes, the policeman asks, are you sure this is where you lost your keys? And the drunk person says, oh, no, this is not where I lost them. I lost them over there in the dark in the middle of the park. But this is where the light is, so I'm going to look over here. And there's a reason why I'm not in comedy. Okay, so what is the whole story about? The story is about sometimes we measure things because they're easy to measure. We're looking where the light is. We're looking underneath that lamppost. Okay? Now, just because we can measure it doesn't mean we should care, clearly, right? There is the case where we may find that what we really care about is something that we find difficult or hard to measure. We've got to go off into the dark in the park and try our best if we really want to make progress on a problem. Okay? The overall thing here is that it is up to you to decide which is which. And it's important to keep this in mind. So we've talked a lot about Twitter's stream and sentiment analysis. So if you're trying to, for instance, understand how people feel about the presidential election, you might be tempted to use internet data like Twitter stream and see what you can determine about people's thoughts and emotions using some sort of sentiment analysis. Okay. But are you going to get a good result? Are you actually going to get at what you want to know, which is how the election was decided, perhaps? Yeah, probably not. People on Twitter are not representative of the entire United States of America, right? And we know that there are bots on Twitter that are amplifying various sentiments because they're being paid to do so. So, yeah, there's no substitute in this case for, wearing out your shoe leather by doing door-to-door kinds of surveys or something like that. Okay? So just because we can measure it doesn't mean we should care. And just because we can't measure it doesn't mean it's not important. Okay. Well, let's say that we are measuring something we do care deeply about. We have a direct measurement. Do we even understand what we are measuring? That is another problem that we often face. So this little story comes from a very famous statistician named Wald, who was consulting with the military during World War II. And the military kept having bombers come back all shot up. And what they did was they recorded where those bombers were being hit. And they put the little dots on the diagram here, right? So the military was saying, well, those are the spots where we should armor the airplane. That's where it's getting hit. So we need to add more weight to the airplane, which is always a bad thing, by the way. Airplanes like to be light. So we're going to add more weight to the airplane at those places to armor them better because they're getting hit there. So the statistician Wald said, yeah, I do not think this means what you think it means. So this is something called survivorship bias. So what we're seeing here are the places you can be hit and survive. The places here, come on. Oh, good. My drawing tool decided not to work. All right, let's see if we can do that. All right. Do I have control now? Yes. All right. It's exciting. So these locations are where an airplane that is hit explodes or crashes. So in fact, what we're seeing here is the exact opposite. The places you want to armor are these locations here. So it's important to understand what your measurements actually mean and how to interpret them. So this is often a very important idea in data science because we learn about the measurements usually from domain experts. It's often the case that you may be working with a field that you are not intimately familiar with. You'll be consulting with somebody, okay? And when you do that, you'd better understand what you can of what these numbers mean. And talking with those domain experts and being in a conversation with them is the way to do that. Okay. We also talked about, are we measuring what's relevant, right? So you may be familiar with something like this. This comes out of U.S. News and World Report. It's the report on, oops. That's what I wanted. Okay. So this is the report on the average class size for UCSD from the college rankings from U.S. News. Okay, great. Let's take a look at this, shall we? So you came into university and maybe you looked at a graph just like this one and you were thinking, gosh, look at all that yellow there. It looks like most of the classes are quite small. So 47% have fewer than 20 students in them. Okay, so maybe just over the line, maybe 25 or something like that is like the average class size. Wow, this is going to be really great. It's going to be intimate. I'm going to have really tiny classes. And if I asked you, freshmen or anybody else, what is your experience of UCSD? Do you think that most of your classes that you're experiencing are 20, 30 students? Yeah, they're not, are they? You are almost certainly not having that experience at all. So when you ask students, you can find out that their experiences typically tend not to reflect this number. So what is going on here? Are the universities all lying, right? Is this all just a big hoax, fake news? No, they are not. So the thing is that average class size isn't what you care about. It's not relevant to a student. Huh? What do I mean by that? So here's what I mean by that. I found a source of the data on class size on collegedata.com, which breaks it down into bins. Okay? So we can see here. So tiny classes, 12% of the university's classes offered apparently are tiny. And a bit higher, a third of them are 10 to 19s, and so on and so forth. Okay? So by doing this, we can go through that list and we can figure out roughly where the mean size is. Or really, what we can do is we can find the median, because the median is the 50th percentile. Okay? So if we add up 12%, okay, and 12 plus 32 is 44%, right? So at this point, we've got 44% of classes covered. And in that next step, the 20 to 29s, we get up to 58%. So somewhere in that bin, in probably the low 20s, is where the median class size is. Okay? So that's what the university reported to you. And what that says is that if you stop a random professor who's walking around the university, at least in non-COVID times, you stop a random professor and ask them, how big is the class that you're walking to right now? The answer will be, median answer was going to be in the 20s. Okay? But that's not what you, the students, experience. You, the students, experience a very different median class size. Why is that? Well, if we try to take this kind of thing, most of the classes are small by number of class, but those classes are small. So most of those classes have very small numbers of students sitting in them. So if you look at butts on seats in the classroom, and you try to find out, as you are sitting in one of those seats, how many butts are around you. Okay, small numbers in the small classes, big numbers in the big classes. So you have to renormalize this into the number of students overall and what they're doing. Okay, so if we just multiply, this kind of 0.12 ratio by 2, the smallest number of students there, and we multiply 10 for the 10 students there by the 0.32 here, and so on and so forth, we get numbers like that. And if we take those numbers and normalize them, so normalize them to the sum, what we get is the percentage of students' experience in these classes. Okay? So in this case, you can see right here, the orange number is in fact the experience of a student. The median experience of a student is that they're in a class of over 100, because that's where most of the students are. They're in those classes that are big. All right, so are we measuring the right kinds of things? Maybe not. This extends into many aspects of science, okay, not just data science. So misunderstanding what the measurement is like is kind of, I would say, a hobby in biological sciences. So one of my favorite Twitter things to follow is Just Says in Mice, which just, all it ever says is in mice, this Twitter account. And it says in mice when attached to a news item which is just totally gaga about some element of science, right? Sight restored by turning back the clock. We're going to engineer neurons to, go back in time to stem cells, and that's going to be able to cure blindness by injecting stem cells into these. Yeah, and as this rather well-known journalist Iglesias said, holy effing F, right? Well, in mice. And there's a really, really big difference between something that works in mice and something that works in humans. So we do use mice as model organisms to understand humans, but even a treatment that works very clearly in rodents is not necessarily going to work in humans, and there's a big, big gap there. So getting excited by a measurement and misunderstanding how that measurement applies is, fairly common. All right, I'm going to take a short little break here, and we will come back with more errors. See you soon.